Motion maps. Think of them as like like if the car had an oil leak, a car that has an oil leak, and it just keeps dripping oil, same drip like every time, like a same amount at a regular time interval. And you can tell then from the trail of oil drops on the ground where the car has been, and you could also judge how fast that car might have been going by the distance between each oil drop. That's what a motion map is. So in our Stomper Car Lab here, um, with this car, it's moving along and it's moving at a steady rate, at a constant velocity. And so the oil drops behind this car are the same distance apart. I believe you have this on the paper already, right? Okay. Okay. So all we're going to do is, as my wife would say, bedazzle this little motion map here. Um, First thing, to make a simple motion map, label your position marks, starting with 0 seconds, assuming that time is in seconds. And that first dot should always be 0 seconds rather than 1. It is at this point, it is at this point right here when we begin caring about the motion of the car. It's when we begin paying attention to where the car is and, for that matter, when the car is. So that's why we always start with 0. Next up, just draw an arrow from one position point to the next. And then I say label the first vector as V1, and then lather, rinse, and repeat. However, labeling the arrows is going to get cluttered. It's going to start cluttering up the motion maps, and so we'll not going to really worry about the labels for the arrows, but I will care about the arrows. These are going to be really boring. You're going to think, my gosh, these are the same things every time. And you'll be right. These are going to be the same things every time. For now. For now. Once we get into accelerated motion, as some of you may remember, when we get into accelerated motion, then these motion maps get a lot more complicated. Acceleration is complicated, but it does make life interesting. And finally, we're just going to do some rearranging here. Well, let's take our velocity equation. Velocity equals displacement over time. Write this down, please. Okay. We're going to substitute something in for displacement here. What are we going to substitute in? Our first equation. Look up at the top right slide, and that's where I get this. So what I'm going to do is I'm going to take all of this, I'm going to plug it in to that displacement symbol there. I'd like you to write that down. You're probably going to end up having to write it off to the side or perhaps down here somewhere. But there's one thing I want you to do, and that is I want you to solve for XF. Algebraically manipulate this so that XF is all by itself. I'm going to make it interesting for you. So here's what that same formula, that same equation looks like with everything just kind of rearranged a little. And I like it when it's rearranged like this. I think you might as well. If algebra gave you any sort of hassle at all, one of the cornerstones of algebra y equals mx plus b. Well, there's a reason for that. The reason for y equals mx plus b is to follow the motion of objects. What your math teacher might call y, we actually have a real quantity for it. Final position, where an object is at any particular time. As we already said, the m, slope, is the velocity of that object. And this b, which math teachers call the y-intercept, we call the starting point. So how far an object is from where it started depends on time and velocity.